Morning. Today we are discussing about RC, RL and RLC circuits. Previously we learned about RC integrator, RC RL circuits, and also we know that RLC circuits. RC and RL circuits are mainly used for filters. Filter means wanted, which have to take only wanted frequencies and neglecting unwanted frequencies. There are so many filters we are discussing today. The mainly RC low pass filter, RC high pass filter, RL low pass filter, RL high pass filter. RC means resistor, capacitor. In between the elements, both are connected in series combination. The low pass filter is a circuit that can be designed to modify, reshape or reject all unwanted high frequencies of an electrical signal and accept or pass only those signals wanted by the circuits by designer. A low pass filter which allows only low frequencies and rejects high frequency components. In other words, they filter out unwanted signal, and any ideal filter will separate pass sinusoidal input signal based upon their frequency. The filters are also named according to the frequency, the range of frequencies that allow to pass through them while blocking or attenuating the rest. The most commonly used filters are low pass filter, high pass filter, band pass filter. A low pass filter only allows low frequency signals from 0 Hz to its cutoff frequency, that is represented by Fc, the point to pass while blocking the higher. In high pass filter, the high pass filter only allows high frequency signals from its cutoff frequency Fc, point and higher to infinity to pass through while blocking any other lower frequency. The band pass filter allows signals falling within certain frequency band to set up between the 2 points to pass through while blocking the low and higher frequencies either side of the frequency band. Band pass filter which allows only within the certain frequency band set up between the 2 points to pass through while blocking low pass and high frequencies either side of the frequency bands. For example, we have to take here low pass filter, the circuit containing of resistor, capacitor, both are connected in series combination. Here the capacitor is used for low frequency and resistor used for high frequency. Used are nothing but to pass through high frequencies across resistor, pass low frequencies across capacitor. In this type of filter arrangement, the input signal Vn is applied to the series combination, that means both resistor and capacitor together, but the output signal is taken across the capacitor only because the low frequencies are flows through capacitor only. The reactance of the capacitor varies inversely proportional to the frequency, that means Xc is inversely proportional to 1 by F, while the value of the resistor remains constant as the frequency changes. At low frequencies, the capacitive reactance of the capacitor will be very large as compared to resistive value of the resistor capital R. Here the input signal is sine wave, we get output signal from the capacitor. Here the low frequency is taken across the capacitor and high frequency is taken across the resistor. The graph is representing like this. The graph is turn breaking frequency on x-axis and output voltage on y-axis. Therefore, the cutoff frequency is calculated by using the frequency at which the maximum output voltage, which drops to 0.707 times of its maximum value, is known as a cutoff frequency. Here, the above the cutoff frequency is known as pass band and below the cutoff frequency is known as stop band. The frequencies which is getting from the output is low frequencies is taken across the capacitor. The graph is representing like this. Here the output voltage to input ratio is calculated by using gain formula. Gain equal to the ratio of output voltage to input voltage. Here the low frequency cutoff frequency of the RC low pass filter is 1 by 2 pi RC. The cutoff frequency of the low pass filter, the frequency at which falls to 0.70 times of maximum value of the output voltage. If the cutoff frequency of the formula Fc equal to 1 by 2 pi RC, here RC is called time constant. Gain, the ratio of output voltage to input voltage, it is represented by capital G, G equal to V naught by VA. The units of the gain is decibels, dB. RC high pass filter. A high pass filter is the exact opposite to the low pass filter circuit, as the two components have been interchanged. That means resistor in place of capacitor, capacitor in place of resistor, as shown in the below figure. A high pass filter is the exact opposite to the low pass filter circuit, as the low components have been interchanged with the filters output signal now being taken across the resistor, whereas the low pass filter only allowed the signals to pass below its cutoff frequency point Fc. The passive high pass filter circuit, as its name implies, only passes signals above the selected cutoff point Fc, eliminated any low frequency signals from the waveform. In this circuit, the reactance of the capacitor is very high at low frequencies, so the capacitor acts as open circuit and blocks any input signal until the cutoff frequency point is reached. In this circuit, the arrangement of the reactance of the capacitor is very high at low frequencies, so the capacitor acts as an open circuit and blocks any input signal at cutoff frequency point to be reached. Above the cutoff frequency point of the reactance, the capacitor acts as reduced sufficiently as to now act more like a short circuit, allowing all of the input signal to pass directly to the output, as shown in the filter's response curve, that means graph. The response curve graph representing like this in high pass filter. Here the above the cutoff frequency is known as pass band and below the cutoff frequency is known as stop band. Here the cutoff frequency is defined by at which the frequency rises to 0.70 times of its maximum value, then it is called cutoff frequency. The graph is representing like this. The frequency taken x-axis and output voltage is taken across y-axis. The cutoff frequency of the high pass filter, the frequency it rises to 0.70 times or minus 3 dB of the maximum value of output voltage. Here high low pass filter or high pass filter cutoff frequency Fc equal to 1 by 2 pi RC. Gain, the ratio of the output voltage to the input voltage, it is represented by capital G, Z equal to output voltage to input voltage, and its units will be decibels. One more passive component we are discussing earlier, that means integrator and differentiator circuits. The RC integrator is nothing but a low pass filter. Here the integrator circuit is connected in series combination with the elements resistor and capacitor and produces an output signal which is corresponding to mathematical process of integration. For massive RC integrator circuit, the input is connected to a resistance while the output voltage is taken across the capacitor, being exact opposite to the RC differentiator circuit. The capacitor charges up when the input signal is high and discharges when the input signal is low. Integrator is nothing but the output voltage is proportional to integral multiples of its input voltages. Here the formula of integrator V0 equal to 1 by RC integral of 0 to time V in with respect to dt. That means the output voltage is proportional to integral multiples of its input voltage. Here RC is known as time constant. An RC integrated circuit is one of the which the output voltage is proportional to the integral of the input voltage. Here the circuit representing the input voltage is taken across, the input voltage is applied to the circuit, the output voltage is taken across capacitor. RC differentiator. The passive RC differentiator is a series connected RC network that produces an output signal which corresponding to the mathematical process of differentiation. For a passive RC integrator or differentiator circuit, the input is connected to capacitor while the output voltage is taken across the resistance, being exact opposite to the RC integrator circuit. In differentiator circuit, the components are interchanged. In place of resistor, we are connecting capacitor. In place of capacitor, we are connecting a resistor. Here, the output voltage is taken across the resistor as shown in the figure. Here, the formula of differentiator V0 equal to RC d by dt of V in. That means the output voltage is proportional to derivative of its input voltage. Another RLC series resonance circuit. In series resonant RLC circuit becomes a frequency point where the inductive reactance of the inductor becomes equal in value to the capacitive reactance of the capacitor. That means XL equal to XC. Here XL is called inductive reactance and XC is called capacitive reactance. The point at which occurs is called resonant frequency FR of the circuit, and we are analyzing RLC series circuit. This resonant frequency produces a series resonance. Here the components resistor, inductor, capacitor both are connected in series combination with AC signal. That means E equal to E0 sin omega t. Here the resonant circuit is said to be the inductive reactance is equal to capacitive reactance. XL equal to XC, that equal to 2 pi FL, that equal to omega L equal to 1 by omega C. Here omega equal to angular frequency, omega equal to 2 pi F. In place of omega we can write 2 pi F, omega L equal to 1 by omega C, 2 pi FL equal to 1 by 2 pi FC, F square equal to 1 by 2 pi into 2 pi, that means 4 pi square LC. F equal to square root of 1 by 4 pi square LC, that equal to resonant frequency FR equal to 1 by 2 pi root LC. This is called series resonance of resonant frequency. By using, we calculating the resonant frequency by using this formula. Here FR equal to 1 by 2 pi root LC or omega R equal to 1 by root LC. L means inductor, capacitor, C means capacitor. Here the bandwidth, the ratio, the frequencies, the difference between the two frequencies is known as a bandwidth. Bandwidth is representing by BW, that equal to resonant frequency by quality factor, that means FR by Q. Bandwidth equal to R by 2 pi L, that means in frequency range in kilohertz. Along quality factor Q equal to omega L by R, that means XL by R, that equal to 1 by omega RC. Finally quality factor Q equal to 1 by R root L by C. In frequency response circuits, current magnitude above or rest or remaining are called sharpness of the resonance in series resonant circuit. The sharpness of resonance is measured qualitatively, is called quality factor. It is represented by Q of this circuit. Parallel resonant circuit. the parallel circuit containing a resistance capital R and inductance capital L and capacitance capital C will produce a parallel resonance. In parallel resonance circuit, we can consisting two arms. One is inductive arm, another one is capacitive arm. In inductive arm, resistor and inductor both are connected in series combination. In inductive arm, which is parallel to the capacitive arm, then it is said to be parallel resonance circuit. The parallel resonance circuit is also called anti-resonance circuit when the resultant current through the parallel resonant combination in phase with the supply voltage. At resonance, there will be a large calculating current between inductor and capacitor due to energy of oscillation in parallel circuits that provide the resonance. A parallel resonance circuit stores circuit energy in the electric field or magnetic field. Suppose we taking the capacitor, the energy charging and discharging both are stored in the electric field. In presence of inductor, the energy will be stored in magnetic field. Here the constantly being transferred back and forth between the inductor and capacitor, which is results in zero current and energy being drawn from the supply voltage. Here the parallel resonance circuit is representing like that, and resistor and inductor both are connected in series combination, and capacitance which is parallel to the inductive arm, and the applied voltage is AC which is flowing through the inductive arm and capacitive arm representing in the circuit. Here RL is inductive XL is inductive reactance and XC is capacitive reactance. Inductive reactance is directly proportional to frequency and capacitive reactance is inversely proportional to frequency. The total impedance of the parallel resonance circuit Y equal to 1 by R plus J omega L plus 1 by JXC. By implementing the equation Y equal to RL by R plus XL whole square plus 1 by R plus XL whole square minus 1 by XC, that equal to satisfy the condition for the resonant, the susceptance part of the value is must be equal to 0. That means susceptance is nothing but reciprocal of reactance. That equal to susceptance equal to 1 by XC, that equal to X by R square L plus XL square. 1 by omega C we can write as omega C, that equal to omega L by RL square plus omega square plus L square. Omega square L square plus RL square equal to L by C. Omega square L square equal to L by C minus RL square. Omega square equal to 1 by LC. In numerator L and denominator L will be cancelled, and denominator will get a single L, that means inductor. Omega square equal to 1 by LC minus R square L by L square. Omega equal to square root of 1 by LC minus R square by L square. This is called a resonant frequency of the parallel resonance circuit. Parallel resonance of the resonance circuit are FR equal to 1 by 2 pi square root of 1 by LC minus R square by LC. Here the bandwidth of the parallel resonance circuit equal to resonant frequency of the circuit to the quality factor of the circuit. Once another words we can write as R by 2 pi L. In frequency, the bandwidth will be R by 2 pi L in hertz. The quality factor of the parallel resonant circuit Q equal to 1 by R root L by C. The frequency response of the circuit, current magnitude above or below related to the sharpness of the resonance. In series or parallel circuit, the sharpness of the peak is measured quantitatively and is called quality factor. Q equal to 1 by R root L by C of the circuit. The main differences between series resonance and parallel resonance representing like that. Here the main difference is the impedance in series resonance will be minimum. The impedance at parallel resonance will be maximum. The impedance at series resonance circuit will be maximum. the admittance at parallel resonant circuit will be minimum. The current at the circuit at resonance in series resonance will be maximum. The current at parallel resonant will be minimum. The amplification of the series resonance circuit is voltage and parallel resonant circuit is current. The Q factor will be the series resonant 1 by R root L by C. Similarly, in parallel resonance circuit, the Q factor will be 1 by R root L by C. The same significance between series and parallel resonant circuit. The power factor will be the series resonant is unity and also parallel resonant circuit will be unity. That means 1. The resonant frequency of the series resonant circuit omega naught equal to 1 by root by LC. Similarly, in parallel resonant circuit, resonant frequency F naught equal to 1 by root LC. Bandwidth is also F naught by Q. Bandwidth will be F naught by Q. The power points of the series resonant circuit omega naught equal to square root of omega 1, omega 2. Similarly, in parallel resonant circuit, square root of omega 1, omega 2. Here the omega is called angular frequency. Thank you.